Question 5 from the 2025 Higher Physics Examination from the SQA. The table contains information about 3 stars in the Milky Way galaxy. We're given a table with the star and its surface temperature in Kelvin, and its radius in metres and its mass in kilograms. And part A says compare the surface temperature of star 2 with the surface temperature of star 1 in terms of orders of magnitude. Well, we can see from the table we've got star 2 here with its surface temperature 210,000 Kelvin. I'm going to compare that with star 1 with its surface temperature of 2290 Kelvin. So we start with star 2 and we put that over star 1 like that. And we're going to have the following. We're going to have 210,000 Kelvin divided by, and we're going to have 2290 Kelvin. Now it's best to put these into standard form. So 21000 is going to give us a standard form of 2.1 times 10 to the power 1, 2, 3, 4, 5 times 10 to the power 5. And we're dividing that by 2.29 times 10 to the power, and it's going to be 1, 2, 3 to the power 3. Now we can ignore the 2.1, the 2.29 because they're roughly in the same ballpark. And we're comparing the powers here. So 10 to the power 5 divided by 10 to the power 3 is going to give us 10 to the power 2. So in terms of temperature, the surface temperature of star 2 is 2 orders of magnitude bigger. So we say 2 orders of magnitude larger. 2 orders of magnitude larger. And we get that from the actual power 10 to the power 2. Question 5 continued part B. Stars emit radiation with a range of wavelengths. The graph shows how the energy emitted per second per unit area varies with the wavelength lambda of emitted radiation from the Sun. Now on the graph above, add a line to show how the energy emitted per second per unit area varies with the wavelength of the emitted radiation lambda from star 2. Now we look at the information from the previous part of the question. We can see that the Sun has got a surface temperature of 5800 Kelvin, and star 2, as we found out, has a surface temperature of 2 orders of magnitude bigger. Now that means it's much hotter. Now the hotter the star is, the graph changes. You're going to have a bigger peak of the graph, and you can see that you're going to have a bigger area of the graph compared to the Sun because it's much hotter. It's going to give out more energy. And also note that the peak wavelength has shifted towards the blue end of the spectrum or the wavelengths. Remember, in this graph here we've got the blue part of the wave here, and we have got the red part of the wave up here, wavelengths up here. That's blue all the way up to red. And you can see from this graph then that the hotter the star is, the more area it's going to have, and the more the graph is in the blue area of the wavelengths. And therefore blue stars are much hotter than red stars. So that's the graph you get, just 2 adaptations to it. You have a much higher peak, and the peak wavelength is going to be nearer the blue end of the spectrum compared to the Sun, and it's got an overall bigger area. Now for part 2 is very similar. It's just for 1 mark. It's to explain why star 1 appears more red than the Sun. Well, star 1 has got half the surface temperature, so it's going to be definitely shifted towards the red end of the spectrum. Remember, the surface temperature gives you an indication of where the wavelengths are going to be emitted from. And because it's going to be a very lower temperature compared to the Sun, then we're going to have a graph like this for that particular star. And you can see once again the area is a lot smaller. It's not giving off as much energy, and also the peak wavelength has shifted over towards the red. So that's why the star 1 appears much redder than the Sun, simply because its wavelengths, because it's a cooler star, most of the energy emitted by each wavelength is going to be more in the red end of the spectrum. Question 5 continued, part C, part I. Exoplanets are planets that are outside our solar system. Star 1 has orbited by a number of exoplanets, and one exoplanet, planet A, has a mean orbital radius of 1.81 times 10 to the power 11 metres and a mass of 6.09 times 10 to the power 24. The mass of star 1 is 1.77 times 10 to the power 29 kilograms. And we've got to calculate for 3 marks the gravitational force between planet A and star 1. From the relationship sheet, we know that the gravitational force between two bodies of mass m1 and m2 is the following. G is the universal gravitational constant, m1 is the mass of the first body, and m2 the mass of the second body, and we're going to divide that by the distance between the centres, r squared. Now we know from our diagram that planet A has got a mass of 6.09, so we'll mark that in there, 6.09 times 10 to the power 24 kilograms. And star 1 has a mass of 1.77 times 10 to the power 29 kilograms. And we know that the radius between the two centres is 1.81 times 10 to the power 11. So using our equation, we can put in our numbers. We can say the gravitational force between these two bodies is m1. We'll just call that, first of all, the universal gravitational constant, which is 6.67 times 10 to minus 11. That's the universal gravitational constant. m1 we can call planet A, so it's going to be multiplied by 6.09 times 10 to the power 24. And m2 would be the mass of star 1, which is 1.77 times 10 to the power 29. And don't forget, we have to divide all that. I put a bracket in it for safety. We've got to divide it all by the distance between the centres squared. So it's going to be 1.81 times 10 to the power 11, and remember, that's all got to be squared. Now if you do that in your calculator and don't make any slip-ups, you'll end up with the following force between these two heavenly bodies of 2.19 times 10 to the power 21 newtons, and that's going to be the value of the force, the gravitational force acting between these two bodies. Question 5c continued part 2. A second exoplanet, planet B, has 3 times the mass of planet A. The mean orbital radius of planet B is double the mean orbital radius of planet A. State how the gravitational force of attraction between planet B and star 1 compares to the gravitational force of attraction between planet A and star 1. Okay, let's look at the first situation. We have this situation here. We have got the first star, which we're going to call M1. That's going to be there, M1. That's going to be M2. And the distance between them, we know is going to be a distance of r between their centres. And right away we know that the force of gravitational attraction between them is going to be equal to G, the universal gravitational constant, M1 times M2 divided by the distance between their centres squared, r squared. And we'll call that for the situation we've got planet A. So that's going to be the force of attraction of planet A from the Sun. Now, if we look at the second diagram, we can see that things are a bit different. We've got a new exoplanet, and the new exoplanet is going to have a mass of 3 times the first planet. So we have to put down there 3m1, and the distance between the centres is now twice the distance from this one here. And this is for planet B, the exoplanet B. Now we can work out the gravitational force of attraction. The gravitational force of attraction for planet B onto the star is equal to the universal gravitational constant, G. M1 will be obviously the mass of this star, which is 3 times M1. So we can put in their bracket 3M1. And we have to multiply that by the star M2, which is not changed. That mass is not changed there. But the distance between the centres is now 2r. And if we square that, we have to have 2r all squared. Now if we multiply this force of attraction between exoplanet B and the star, we have 3 times the universal gravitational constant, M1 times M2. And we have to divide that by this part here squared. 2 2s are 4, and we've got r squared. Now we can take out a common factor here. We can see that we have the following situation. We have 3g m1 m2, so we can take out the 3 and we're left with the g m1 m2, and we can divide that by taking out the 4 here and divide by r squared. And if you look very closely, you can see the following. You can see that gm1 m2 or r squared is really equal to the force of A experiences with the star, gm1 m2 over r squared. So we can replace that bracket by the following. We can say it's going to be 3/4 times the force experienced by the exoplanet A. So we have our answer there. We have that the exoplanet B, the force of B, the gravitational force of attraction experienced by B, is going to be equal to 3/4 the gravitational force experienced by A. Question 5c, part 3. The exoplanets orbiting star 1 were discovered using the transit method. The brightness of the light from the star is recorded, and a dip in the brightness is recorded during the time it takes the exoplanet to pass between a star and an observer. The table below gives the information about the exoplanets A and B. And we can see we've got the star, like this, if I can do a wee sketch of the star. And we've got the following. We've got planet A, and we've got planet B. And you can see that planet A's radius is bigger than planet B's. But the time it takes for planet A to move round the star is going to be 4 times faster than planet B. Planet B is orbital period, that's the time it takes to make one complete lap, is going to be 4 times 10 to the power 8 seconds, and planet A is going to go through a lot quicker, 1.4 times 10 to the power 8 seconds for one complete orbit. So the time planet A passes in front of the star will be a lot quicker than star B, than planet B. So what do we expect then? Well, we can see planet B, which we've got here, it says here, add a line to the graph to show the brightness varies with time as planet A passes. This is going to be planet B, and it's going to pass like that. And planet A has obviously got a bigger radius, going to cut out more of the light, therefore you're going to have a bigger dip. And because you're going to have a bigger radius, you're going to have a bigger dip in the brightness graph. It's going to block out more light. But it's moving faster past that star, so we're going to expect something like this. We can expect the star planet A passes, we can expect A to do this. It's going to have a bigger dip, but a much faster time like that. And it's a possibility that in the course of this here, you might get even more transits. So you might get something like that. It might dip down again. And you might get about 4 of those in the given time like that because of the situation. But the question really just asks you for 2 things. It's for 2 marks. And all you have to say quite simply is this, that the brightness is going to dip down. So we can have this part here. And the time it takes to pass is going to be a lot quicker than star B, and therefore you can rely on just putting in that graph there. But as I said before, you're going to get maybe more dips because star B is moving round the star much quicker, therefore maybe catch up with it. But it'll be suffice to give this particular graph here like that, I think. Just stay like that and levelling out along here like there.